So if the bug is on the record, so let's place the bug on the record. And records have a hole in the middle. That's so you can line it up on the platter so it can spin. I hear records are all the new fads again and people have them, but I think it's kind of silly. It spins this direction. So you can imagine your bug is over here. You're told in the problem that this is 12 centimeters. Probably going to have to convert that to meters. I can't imagine 12 centimeters working out for you. But we are told that it is spinning at 33 RPM. What you may not be able to do is figure out how to take that and turn it into meters per second. I'm going to help you. In one rotation, the bug has traveled 2 pi r meters. Do you follow what I just said? So in one rotation, that's how far the bug went. But the bug did 33 of these rotations and did them in 1 minute. RPM to meters per second. There are other ways to convert this to. I'm just throwing down one that I think is simple enough for most of you to understand. And this is going to give you your value in meters per second. So what I'd like you to do real quick for me, since it's sitting right here, and I think it's appropriate that you do so, what would be an appropriate free body diagram for the bug? And you have to solve this problem. And the solution to this problem involves it being a Newton's second law problem. We know it has to be second law because the bug is traveling in a circular path, which means it has a centripetal acceleration. You're going to need a free body diagram to understand which force is causing it to travel in a circle. I'm very interested in seeing what you get here. Just a free body diagram. Some of these things I think are obvious, but sometimes things that I think are obvious are less so. Just look at the bug for a minute. Clearly, weight's acting downwards. Right? No doubt. We have rules. We can follow the rules. And is there a conservative force acting on the bug? Yeah, weight, always. Sometimes it's relevant, sometimes it's not. It's relevant here. Is it in contact with the surface? Sure is. It's in contact with the record. That's got to provide an upward force perpendicular to the surface. That's got to be a normal force. Is there any cable connected to the bug? No, so there's no tension. Any likelihood of a resistive force acting on the bug? Very likely. The whole problem asks about something dealing with friction. So very likely there's a resistive force acting on the bug. We have to figure out the direction of that resistive force. I don't think it's a surprise. The only way the bug travels in a circle is if there's a force pointed towards the center of that circle, suggesting that there's got to be a force in this direction. It's going to have to be. What force is that? It's friction. If there isn't a force in that direction, the bug travels on its last straight line path. It slides off the record. So in my free body diagram, those are our forces acting on the bug. This problem is not challenging. It's hard maybe because you haven't done a circular motion problem before. But the rules for how we apply Newton's law are all the same. The reason I want to do this problem is because I'm afraid you guys don't know how to deal with RPMs. I'm also afraid you don't know how to deal with inequalities. Some of you might be able to, but I know I have a subset of you who don't. And this problem involves inequalities. I want to show you how to do something called preserving the inequality. It's a phrase I made up because I need to have something to call it. And like I said, feels like whenever we have a name for something, we feel like we have more control over it. I want you to be able to preserve the inequality, which means I want you to create an inequality through substitution. Everybody understand? That's what the point is. Preserving the inequality gives you an answer that will be an inequality. So not only do you know what the threshold is, but you know whether you have to be above or below that value. It's not always obvious. For this one, I think it is obvious, but it's not always obvious. So I want to show you how to do that. But we're not quite done with the Newton's law part here. So let's finish off the Newton's law part. Net force in the x direction equals MAC. I'm thinking that's friction, which equals mv squared over r. I could do two substitutions at once. You're okay with that, right? This is a centripetal acceleration problem, so the acceleration is modeled by v squared over r. Good so far? All right. That's net force in the x direction. Net force in the y direction has to be 0, which means normal equals mg. There, we've done all the things that are part of our force concept model, right? Drew a free body diagram, identified the forces, applied a coordinate system to that set of forces, and then applied Newton's laws, subbing in the forces for the net forces. That's a lot of words that use the word forces in it. Keep going. Remember, at the end of using the force concept model, you are left with a relationship or two that may or may not be used to solve your problem. I think we can probably solve the problem with the information that's here. We're gonna have to bring something else to bear, and that is for static friction, we have an inequality. The problem asks, what is the minimum coefficient of static friction for the bug to stay on the record? So the problem wants us to have mu equals, or mu is less than, or mu is greater than something. Now, this next part is how you deal with these three things together while preserving the inequality. To preserve the inequality, you need to ensure that your substitutions always substitute into the inequality. So far, we've been substituting out of the friction equation. We're going to sub into the friction equation, meaning we make this the equation that we substitute into as opposed to out of. So I have an expression for friction. I'm going to substitute it into this equation. So m v squared over r is less than or equal to mu s times n. I've subbed into the friction equation. I'm going to continue to do so because I know more about the normal force as well. So I'm going to take this and sub it into my inequality. Again, this preserves the inequality. M v squared over r must be less than or equal to mu s mg. The first thing I want to point out to all of you is that it doesn't matter what the mass of the bug is. That happens a lot. You'll find mass cancels out in a lot of circumstances. So if you're not given a mass, it's likely you don't need it. So it seems to me that mu s has to be greater than or equal to v squared over gr. I've preserved the inequality now. Remember, the problem asks, what is the minimum value for the coefficient of friction? If you had just set it equal to, you wouldn't know if you're at a minimum. We now know we're at a minimum because this says that the coefficient can be greater than this number, but it can't be less than some number, right? That's what greater than or equal to means. So it tells you quite clearly that you are at a minimum. Otherwise, how would you know you're at a minimum? This preserves the inequality, letting you know you're at a minimum or a maximum. It's especially true if you don't know whether this is a minimum or a maximum and you're trying to find out. So I'm going to strongly encourage you to, when you have an inequality, and this is the only inequality we have in this class, that you substitute into the inequality to preserve the inequality as a part of your answer. I have another problem I want you to look at. There's actually three. I don't know if we'll see all three of them, but I know y'all made fun of my helicopter. Go ahead and make fun of my car. I have a car. It's driving on the road and there's a dip in the road. The car has the cruise control set, so the car has the same velocity all the time. Well, I'm sorry, let me say that different. Has the same speed all the time. At some point or another, the car will be at the bottom of the dip. Could you draw me a free body diagram for the car, paying close attention to what the size of the arrows should look like? When it's at the bottom, right here. I'd like to know what the free body diagram of the car would look like here. In some cases, you guys are fantastically brilliant, but in other cases, sometimes I think you are on autopilot. Is there a downward force acting on the car? Sure. Simple enough, right? Now, normal force got to be acting on the car too, correct? But before I get to the normal force, some of you have sideways arrows. That's fine. It doesn't matter to me. If you decided there was some friction, great. But you better have another arrow here. I said the car is traveling at a constant speed. It shouldn't be accelerating left or right if it's at a constant speed. So if you're going to have that, fine. There's probably is friction or air resistance acting on the car, but then you better have the car's engine pushing it forward. Fair enough? It's the normal force I really want to talk to you about, because the only way this car successfully makes it through the dip is if the upward force is greater than the weight. This car's traveling in a circular path, right? That's a circular roadway. If the forces were balanced, the car will travel in this straight line. That's probably not the way you would like to go. In order for the car to successfully make it out, the upward force from the ground is going to be greater than the weight. You feel this whenever you've driven through a rut or you've been on a roller coaster. You feel heavier at the bottom. That's not really you feeling heavier. It's the bottom of the track or your car or your seat pushing upwards on you to make you travel in a circular path. That's why you feel heavier at the bottom of any of these kinds of dips. At the same time, you understand that there's the other version of this, right? I mean, if you're at the bottom of the dip at one point, it's possible that there's another roadway where you might be at the top. Can you real quickly kind of draw what that must look like then in order for us to preserve the same kind of relationship? It's not worth spending a lot of time waiting for you guys all to draw this. I'm assuming you did mg downwards. And if you drew a force left and right, they're less important right now. You understand that, right? They're going to be balanced out. It's going to be net force equals 0 in the x direction. But did you make your normal force smaller? I hope so. Now, bear in mind, net force equals MAC in the y direction. I'm going to make downwards positive, purposefully. I'm going to make the positive direction the direction of the acceleration, which has to be towards the center of the circle. So that's going to be mg minus normal equals mv squared over r. I know when you look at this, you see a lot of letters, but you should look closer. You understand these letters represent values, correct? This is a constant. It's not changing, right? The weight of the car stays the same. Mass of the car stays the same. True? Radius of curvature stays the same. The road doesn't change while you're driving on it. That means these two values can change. You could speed your car up or you could slow your car down. Do you understand that you are taking something away from the weight here? Right? You see that. The value on the left is less than the weight. You have limits here. If you go too fast, the normal force will go to 0. Right? The faster you go here, the bigger this side has to be. The biggest the left side can be is when the normal force is 0. You see that has to be true. This is a constant. You're subtracting a number from it. The biggest that side can be is when I subtract 0 from that number. Everybody understand? That means if you go any faster than that, you lose contact with the ground. That's the definition of jump. So if you go too fast, you're no longer in circular motion, you're a projectile. This is a limiting quantity. You understand that we dance around limiting quantity problems all the time. This is a version of this. The normal force has a minimum value and it's 0. The ground can't pull down on the car. Roller coasters, sure, we'll lock the cars to the track. We'll pull down on them. We'll exceed this. That's to make you feel like you're being thrown out of the roller coaster car. They do it all the time. But in this problem, in your car, you don't want that to happen. So it's probably in your best interest to stay below the velocity where that will occur. Unless, of course, you want to jump your car. Cars don't jump for real life the way they do in the movies. They use cables and cranes to make the cars jump the way they do in the movies. Please don't jump your car. You'll likely land on your front bumper, and that's not very nice or fun. I've been in a car where that's happened. It was not enjoyable. I was not the driver. A long time ago, they had this ride at Busch Gardens. It was a consistent vomitorium all the time because it had a really small radius and it made people relatively sick relatively fast. There's versions of this ride everywhere. The teacups are a version of this ride. Mission Space is a version of this ride. But the one you tend to see at the state fair is the one where you can actually be kind of stuck to the wall and not slide down. Guys, how many of you have ridden a ride like this? There's several versions of it. There's also the kind where the whole thing is exposed and open air, and then the whole thing rotates kind of like that and spins the people around. You guys have seen these? Okay. This is a state fair kind of thing, or a county fair kind of thing. We like these rides, kind of. But could you do me a real quick favor? If this person is truly stuck to the inside wall, what do you think the forces are acting on them? This is problem number 33 in your homework. 30. Is it 33?
I thought that only went up to 22.
I don't know. What's the last one? 22. It's problem number 22 in your homework. All right, look. You want to see this if you want success on your homework. Weight downward, sure, right? A lot of you screw the next two up because you just can't believe it's true, but it's true. You're in contact with the wall. Normal force has to be this way. Normal force is causing centripetal motion. You don't slide down only by the grace of friction acting upwards. All right.